So recently, it's been hard to go a couple of days without seeing articles on the news about the Zika virus. This is similar to the Ebola outbreak of 2014, and these diseases are capturing the attention of the media, the public, as well as our nation's public health officials. So our team asked ourselves the question, how can we better contain the spread of epidemic outbreaks? So good morning, my name is Emily Chen, and along with my team members, Allison, Lena, and Chloe, we're here today to present to you our project, Going Viral. So the purpose of our project is to create a public health policy tool which is able to curb the spread of a disease through efficient resource allocation. And there's really three main aspects to our project, which my team members will elaborate more on. The first aspect is to use network theory in order to create a model that can model the spread of a disease through a group of cities. The second aspect is to incorporate information from this network model into an optimization algorithm that seeks to maximize each city's population's rate of recovery given a set amount of funding. And finally, the third aspect is to incorporate both the network model as well as the optimization algorithm into a software, onto a web interface, that then public health officials, such as the CDC, can use in order to better allocate resources. So now that I've talked about the fundamentals of our project, I'd really like to lay a foundation in network theory. So actually, the basis of our project falls under the category of network medicine, which is the use of network theory in identifying, preventing, as well as treating diseases. And network theory really uses graphs, such as the one that used to be behind me. So actually, graphs show the pairwise relationship between entities called nodes, and these pairwise relationships are represented by edges. And edges can either be unweighted or weighted, depending on the strength of a relationship in an underlying parameter. So these edges can also be undirected or directed, depending on the orientation of a relationship. Now nowadays, with the increase in availability of disease spread data, network theory is becoming increasingly useful in its use in preventative medicine. So actually, our group in particular used the Google Flu Trends dataset, which uses weekly data showing the proportion of a population infected from a period of 2004 to 2015 across major US cities. Now that I've spoken a little bit about the concepts of network theory, I'd like to pass this on to Allison, who's going to speak more about our epidemics outbreak model.
Thanks, Emily. So throughout the year, we've built off of research of members of Penn's ESE department. And in our model, cities are represented as nodes in a directed, weighted network graph. Within each city, we observe an SIS epidemic process happening. SIS stands for susceptible, infected, susceptible. So this means that individuals within the city are either in a state of being susceptible to the disease, in our case the flu, or infected by it. Once they recover from the disease, in SIS, they return to the state of being susceptible, meaning they could get the flu again. The equation you see on the screen now represents how we calculate the different relationship weights between cities in the network. So as Emily mentioned, different nodes in a city in network theory can have different influences on each other depending on certain parameter values. So the key parameters in this equation and our model in general are the PI values, which are the proportions of populations infected at each time step t, the delta I values, which are the recovery rates for each city, and the beta IJ values, which are the relationship weights from city I to city J. So next, in order to be able to solve the ultimate resource allocation problem, we first needed to calibrate all of these different parameters in our model. The equation you see here represents how we predict the proportion of population infected at each future time step based on previous data. So in an ideal case, if our model were entirely accurate, and we were assuming that we're allocating $0 in additional resources, we wouldn't be improving the recovery rates at all. And that would mean that this predictive equation should return exactly the same data that we have in our original data set from Google Flu Trends. So to calculate the different parameter values that would make this the case, we first converted this equation into the matrix format that you see here. We used MATLAB to plug in data from Google Flu as the p-values in the vectors, and then solved for the central matrix of beta and delta values. When we tested these results, we found that we were getting more accurate results than we had been when we used certain model simplifications and assumptions, but it wasn't quite as accurate as we thought we could get. So we decided to take it a step further and wrote an optimization algorithm that would iteratively solve for the best natural recovery rates for each city. So the way this algorithm works is that we look across all possible sets of delta values. And for each city, across all time steps, across all cities and all years, we calculated the predicted portions of populations infected that our model would give us at each time step. We then compared this to the set of actual data from Google Flu Trends, and we found a set of delta values that would ultimately minimize the absolute difference between the actual data from Google Flu and what our model predicts. And once we did this, we were able to select that delta set that would generate curves like the one you see here. So this red graph is what our actual data from Google Flu Trends is for the proportions of populations infected. And the blue graph, which is now shown on top of the red, is what our model predicts. As you can see, these are pretty closely aligned. So now that I've talked a little bit about some background of our model and how we improved its accuracy, Lena's going to go into more detail about how we actually solved the resource allocation problem.
Thanks, Allison. So Allison went over exactly what the predictive model looks like, and now I'm going to talk about how we use that for the resource allocation model. So first, our resource allocation model is a convex optimization problem. We decided to use the convex optimization problem because the local minimum is also the global minimum, making these kind of problems really scalable for large data sets. We also can use the convex CVX package in MATLAB to code this problem rather conveniently, and you'll see a subset of our code there. To the right, at the top of the screen now, you'll see also what the representation of the code and math theory. So basically, the objective function is that we're trying to minimize the spread of the flu, subject to two constraints. The first constraint is that the allocation of money to each city, which is represented by GI, the sum of all of them has to be less than some inputted total budget C. And then the next constraint is going to return our output, which is the improved recovery rate for each city, delta IC. And it has to be greater than some natural recovery rate, which Allison talked about how we calculated, and less than some maximum feasible recovery rate for the flu. And just to summarize, how this model works is that a user inputs a total budget to allocate to different cities, and then the output returns the optimal resource allocation to each city, as well as the improved recovery rate for each city. Okay, so now that I've finished talking about the math behind our model, we're going to move on to what our public policy tool looks like. So we tried a lot of different iterations to get the tool running up on a server and on domain, which we eventually successfully did. And I'm going to talk a little bit about the systems design and how a user would use this tool. So a user goes onto the website and they can input a budget, a year, and a US cities network. They input this into the front end of the website, which is coded in HTML, CSS, and JavaScript. This connects to Python, which helps us connect to the back end, which is in MATLAB. MATLAB connects to the CVX package, which returns the answer to our resource allocation problem. And then we parse the data and visualize it in a way that the user can really use. So now I'm going to pass it on to Chloe, who will show you what our tool looks like.
Thanks, Lena. So now I'm going to give a video demo of our web interface. So now I'm going to give you a video demo of the website. Hopefully. No? Just talk over. Okay. All right, we're going to do this in person. Okay, so this is the homepage of our website. Gives a background information on our project, some of the math behind the model. The next tab is...
Graphic proportion of the population infected by the flu out of 100,000 in particular cities during a selected flu season. You can also graph multiple cities or multiple flu seasons on the same graph to compare trends. Demographic information on age and gender breakdowns for the cities is also available at the top of the page for the user to better interpret the data. The heat map tab allows users to visualize the correlations between the flu data of cities in the network over a given period of time. The user can select cities on their own or choose to look at a pre-selected set of related cities. The resulting heat map will show how correlated the flu data trends are for the cities in the selected network based on the size of the circles over each city. The exact influence value for each city can be found by clicking on the circle. These values increase as a particular city's data becomes more strongly correlated with that of other cities in the selected network. Finally, the main portion of our website is the resource allocation tool. Users can input their budget into the site, select a region and a flu season, and see the results of the resource allocation after submitting. The chart displays the optimal budget allocations to each city in the network, the natural and improved recovery rates for each city, the number of people saved, and the average cost per life saved. Below this information, the user can graph a particular city to compare the infected populations if the resource allocation were applied compared to allocating no additional resources. The red graph depicts the number of people infected without the resource allocation, and the blue graph shows the result of the allocation.
Okay, so how can we think about this on the scale of our project? So for example, we would have somebody like the CDC who would input their flu data into the model. Then they'd use half of this data as training data in order to figure out the natural recovery rates and the beta matrix. They'd use the other half of the data then as the testing data in order to confirm the accuracy of these parameters. Then with these parameters, they'd be able to use it to predict the flu seasons, the infection rates for the flu seasons and the next couple of seasons. Finally, they'd use the resource allocation tool, which we just showed on the web interface, in order to figure out how to best allocate their resources in order to combat these infections in the coming flu seasons. But now let's think about our project on a global scale. So we'd really like our project to motivate the CDC in order to centralize their data so that they can best figure out how to visualize their data and allocate their resources. But even more so, as Emily mentioned in the beginning of our presentation, this can be applied to other diseases as well. And so the Zika virus right now is a huge problem, and they're not really sure how to understand how big of a problem it's going to be, and so our tool could be helpful in that. It can also be helpful for the Ebola virus, which there's limited resources in these developing countries. And finally, it can be used for understanding violence spreading and understanding these interactions between people and how they spread within close proximity. And so there are a lot of diseases in this world and limited resources. And so in Team Going Viral, our goal is to understand these diseases and approach global health from a data-driven perspective. Thank you. And now we'll open for questions.
How do you predict a specific virus how fast it's going to spread if you don't have background data like Zika was a new virus? So until it has some data, you couldn't really predict its spread, right?
Yeah, so our network is, that is a certain limitation to this model, is that you do need a significant amount of data to be able to train it. But the nice thing about this model is that you can use similar data from other diseases that spread in similar manners, such as HIV or AIDS, in order to develop the underlying relationships and the different network that it spreads across. So you can really establish that with other parameters and data that these organizations would have to determine the spreading process, and then apply what smaller amounts of data that you have to the actual prediction in terms of what you're expecting for populations that are infected.
You can start with something that you think exhibits the same characteristics, and as you go along, you can determine how good or bad your assumption.
Yeah.
Yeah.
And another thing that could also be helpful is understanding like transportation networks different ways that it could possibly spread. So that was something that we had considered in the heat map version, our tab of our website, which we had different selected networks like the Amtrak Northeast Corridor, busiest airplane routes. So really trying to understand different ways that it could spread. Yes.
Yeah, so often when you do this type of data analysis, surprising results come out, and the factors that you didn't expect to be factors end up matter. You guys have a lot of time to play with the data. I'm curious if you saw anything that really surprised you, like February 17th was the day everybody got it, something like that. I'm just curious.
Yeah, so one thing that was surprising when we were using the heat map tab was that depending on which data range you were looking at, or like which, if you chose a specific time window, you'd see certain cities would be more correlated or more influential in a network than others. So for example, sometimes we'd see that Baltimore would be the most influential out of a network of on the Northeast Corridor, which initially didn't really make a lot of sense to us because we were thinking like, oh, it must be New York or Boston or much bigger cities that would be more influential, but it just happened to be the specific time step that we were looking at that it had more people infected in their city than in another time step where New York would be more influential. So that initially was kind of a shock for us, and it took a little bit of playing around to figure out why that was happening.
I think another interesting thing that we noticed in a similar vein on the resource allocation, so if you think about the same type of Northeast network with New York and all those cities, New York has a much larger population and its natural recovery rate is somewhat lower than some of the other cities. So even though you might expect they should be getting a lot of the resources, we actually discovered that it's not necessarily cost effective, depending on your budget, to spend a lot of money in New York, because in relative terms, you're not going to save as many people as if you spend it in smaller cities.
Yes.
Did you consider other applications outside of health where going viral might be applicable?
Yeah, so one thing that we talked about when we went to test it on our users, so we went to different health professionals at Penn Med, and one thing that somebody brought up to us is this idea of violence spreading, and how it's really kind of spreads in a similar manner of like it's people to people. And so that could be another way to model like how certain outbreaks might happen in different cities, because it's really happening in close proximity. And you notice with like a lot of like protests that happen, it generally happens like from place to place. It doesn't happen like in New York and then in California or something. It happens like close nearby. So that's another application, just really understanding people interactions.
How about non-health? What about marketing, for example, spread of a fad?
Yeah, there are a lot of examples that we talked about with other researchers, things like this, like for example, new technologies, like like the iPhone, for example, maybe could have been modeled as sort of an epidemic spread. So there are definitely things outside of the health space or even like a human lives context that the same type of epidemic spreading model could be applied to.
It's like computer viruses.
That could be. With computers, with social media, there's like a different element to it too. That is something that we'd have to consider, just because you can have things that are, it's a little bit more random when you have a social network, because I could be friends with somebody that's in Australia, but it doesn't mean that I would necessarily give them the flu if they lived in Australia, if they were like that far away in proximity. So there's some other aspects there. But computer viruses could also be something we could look at. Any other questions? Okay, thank you so much.